Okay, so welcome everybody to today's NCTS second, we just finished one lecture, and our second district lecture is given by Professor Horng-Tzer because I was just about to host this. So let me introduce Professor Yang in Chinese, in Mandarin. Okay.那杨洪哲院士他是我们台大的系友啊，他1981年he graduated in 1981 from National University, and then he graduated from Princeton. 然后他是我们2014年台大的杰出校友，好，那也是我们理论中心的 NCTS scholar， 还是我们的咨询委员的样子哈。是我们的咨询委员，然后他有获了很多奖项，他是曾经获Horng-Tzer奖，还有麦克阿瑟奖，也是美国国家科学院院士，美国艺术及科学院，还有中研院的院士。好，那他的研究领域呢是数学物理。然后分析跟几率论领域，它是数学物理分析跟几率论领域的领导的那个 leading expert 哈。那他的研究成果影响了几率论、随机过程、随机矩阵，还有非平衡态、统计物理和那个量子力学等等。好，然后是我们现在影響层面最深最廣的數學家之一。好，那他今天呢，so the title for Professor Yang's talk is the random matrix theory and the application to statistics. Let's welcome Professor Yang.
您的 introduction. So I think I was English. But the first thing I want to tell you is it's in probably to disappear. The education to statistics is high. So there's a holy title. Half of you here. But anyway, so I will talk about the metrics and the application of statistics will not say so much in this lecture, but so I think the second part, especially toward the end of my own work, is with Professor Lu, and that was inspired by how in the middle and engineering. So, all right. So let me start with the introduction of the random matrix. So the most the simplest one is for the Gaussian automaton ensemble, and the standard example is the data. And this is the Gaussian automaton ensemble equals 1 beta equal 1. I mean, they don't, you may see the data here in various places, but it's really for purposes of the think about it, there's a number variable or something different at the moment. And the simple thing is that you pick Gaussian random variables, symmetric, so it's Xij, Xji, and then you have the mean 0 and the variance 1 over n. So variance 1 over n is normalization. This is actually one of the simplest example of the random matrix is think of it as everything is Gaussian, it's symmetric, and normalized. And then there's something called Wigner ensemble. The Wigner ensemble is with all the Gaussian conditions. the Gaussian is normally distributed. So just replace this Hij by some different distributions, and those are could be Gaussian and it's for the original. And then the third example of random matrices example is adjacency matrices of random graph. So you know, I before I worked on random matrices, which is about 15 years ago, nobody little about command authorities. And then they go, I find this is actually a problem in my application because a random graph, anyway, any graph is a matrix. It's just adjacency matrices become a matrix. So a graph in the matrix is one-to-one correspondence, and so a random graph in the random matrix actually are the same thing, which is adjacency matrix is you put one when there's edge between I and j, and you put zero when there's no edge between I and j. So this is another example of random matrices. So you can see that the one big reason to study the random matrices because we can study random graph. And now, so the application of random matrices because now you know you only want to solve the equation y to the this kind of equation, and we state random matrices. So so there are many things about this linear integration, high dimension. High dimension linear integration is always connected with the matrices. That's why I think historically it's quite funny. I started looking at this problem from this point of view. Here I was studying the random matrix, and then I think that was about 12.
这是你那个出那个
What?
那个声音刚刚都不太那个，
好像不要移到
靠嘴巴一点。
I see. So I think that there's another way to fix this problem.
If I stand on this side,
And then look at this, then it will be okay, right?
不要。
All right, so, you know, the reason is because I know all of this is problem. All right, so, so another thing, people, you know, when I started random matrices, it's in about 2007 and 2008. I didn't know anything about the regression about the statistics, but later I find that the people in statistics, in the old days, they only care about, they don't care too much about this random matrices, but because high dimensional statistics will require knowledge about random matrices, really because you want to solve these linear regression problems. And so that's why, so you see a lot of cases, some so-called sample covariance metrics here, and this becomes as a last interaction between the random matrices and the statistics problem. And now the last example I would like to say is the so-called neural network. The neural network, it's this is the variables here, and then all these lines are this Gaussian. You can use Gaussian, you can use non-Gaussian case. So a neural network is actually a multi-layer example of random matrices. So at the end of the second half of this talk, I will talk about this one case or just a two-layer case. And two-layer case, it becomes a nonlinear random matrix. So you will see that the nonlinear random matrix is actually a special example of neural networks. All right, so so this was the well-known theory about the well-known fact about random matrices. It's the Wegener invent this Wegener semicircle of really like the symbolic eigenvalues. And now you put eigenvalues, then you find the most eigenvalue almost all of them is to be minus 2 and 2, and they may be outside. And if you look at density of eigenvalues in this semicircle, this actually was proved by Wegener in the 1950s. So it's actually before I was born. This was proved by Wegener, and then but he only proved that this in the sense that the density converges, so you don't really know the any fine structure. And later on, people ask the question about it's actually not actually the question in physics actually would like to understand what's the space and statistic between the two eigenvalues. So you can see that the density is a much easier question than we are asked about the gap. So about the gap statistic, then this is much harder. And this was computed by the famous Japanese group of Jimbo, Miwa, and Morisato. We were first computed by Goldin and Maynard, and Goldin and Maynard did this calculation, and then it was connected to the Penavere equation by the Jimbo, Miwa, Morisato. All right, so you can also now the question is unexpected. Oh, that's I figured out. Sorry. Sorry. All right. Now, okay. So now Wigner has an idea. Says Wigner believe that this eigenvalue statistics or random matrices is actually a new probability law. It's a new probability law in the sense it's not Gaussian and it's not Poisson distributions. And then the Wigner believe that many systems in the universe actually obey this law. And so he believed that this is a universal probability law for systems with the high correlations. So think about this. If you look at the, I think it's still not working because well, I have to.
调整一下就好，然后再调整一下。
我转过来，我转过来。
是一个不错，你把它放掉。然后你线上是完全可以这样。它上面
No, that's okay. That's okay. I think that's.
就是太低了吧？
Anyway, oh, no, it's over. I think the point is I have to turn my head and listen to speak.
用手指跟针传。
Oh yeah, 用手指。
对，用手指。
Yeah, that's right.
先把它向你的手。
因为它更喜欢。
Can you hear me? All right. So this seems to be better. All right. Okay. So now we can say this is universal probability law in the sense that we know essentially the theorem and also the Poisson statistics, but we can say it's now for system with high correlations, and this will be the impact of statistics. And then the question, I think I mentioned this a few times. The question is how much this is correct, and in particular, you can ask that you can ask the question, for example, like in the original matrix, this is the Gaussian case. This Hij is Gaussian. If this Hij is not Gaussian, for example, if this plus minus 1, then whether the eigenvalue statistic would be the same as Gaussian. And so this was the famous question for a long time, until about 10 years ago, something 15 years ago, 10, 15 years ago, depends on how you count it. And I want to emphasize, this is just a special case of Wigner's graduation, because what he want is a much more general fact. And so the conjecture was the eigenvalue statistics has nothing to do with the metric element statistics. This is a type of statement called universality. The eigenvalue statistics, local statistics are independent of the metric element. But you see that I want to mention two things. Actually, in the case of real matrix and complex matrix, you have different law. So it depends on the symmetry class that you will independent metric law. And so, and the other thing is the George Uhlenbeck actually didn't like this Wigner's idea. He said that the actual global law means when I say local law means this means local law. This means what's between the two eigenvalues. The global law is a semicircle. So a semicircle is not universal. If you have a different matrix, so the semicircle sometimes will change. So Uhlenbeck didn't like this idea, but actually this was proved to be correct. And so I would say a few words they don't. And nowadays the other question people are asking is what about statistics at the edge? Statistics at the edge is you have subtract these two and you scale by NU2 the conventional Tracy Wheeler law. And these I mentioned previously, is covariance matrix X star X, but you can also put the diagonal matrix in the middle. And then you want to understand the spectral statistics of this model. And in the case you also want to study sparsity. And now, actually, if you look at the the statistics literature or this machine learning, whatever, signal processing sparsity is almost everywhere. Freedom is most of the time you only most elements are zeros, only have a few, which is as meanings and those sparsity is almost everywhere. And now today I would say in particular some more about eigenvector behaviors. And the reason the eigenvector are important is because the eigenvector will appear in this something called principal component analysis in statistics. So whenever you saw the people who I say the principal component analysis, it means the eigenvector, the principal eigenvector of the measures. And so they are basically the same thing. And so that's why a lot of these random matches was using statistics because it's especially because this principal component analysis is just really just about the eigenvectors. All right. So do I have a time? Oh yeah, okay. Oh, so when did I start?
Science.
Okay. So okay. All right. Okay. Now about eigenvector, you can see the eigenvector is something called completely localized. Completely localized, this means that the eigenvector is L infinity norm is less than n minus 1 because these eigenvector are normalized in L2. So if it's completely flat, then each one squared will be 1 over n. And so the completely localized means it's almost 1 over n, so it's anything epsilon minus 1 and with some small error. Actually, if you look at some of the students, some of the recent results, they can actually, they always replace that n minus 1 times log n and become much precise. I still say that this whole definition is called completely localized, is almost n minus 1. And then there's another concept called quantum unit capacity. So this means that the eigenfunctions are completely flat. This is something people like Peter Sun and Rudnick, they are very interested in this kind of question in differential geometries. But we just follow this name and this called quantum unit capacity. We just say the probability version of this. So eigenvector is completely flat. That means each eigenvector component, alpha component, and you multiply by n, and you believe this is 1. So subtract 1 and you take an average divided by a. So if this goes to 0, then you say the eigenvector are completely localized as long as, of course, the a has the number of sites has to be large. And you call the eigenvector satisfy the probabilistic GUE. This means the eigenvector are completely flat in the sense that you are averaged over enough number of sites, then it becomes become completely flat. This is something called a probabilistic GUE. It's a sort of this. You can see that these two statements are the same because this volume form becomes the summation divided by 1 over a, and this test function just is set. All right, so this is just one eigenvector, but in the random matrix case, you can ask the general distribution of several eigenvectors, and you can also ask the central idea. So there are various questions one can ask. Now, so let me just say, just select a few results, and I will talk about. I think I probably will drop the random block parts and just talk about random matrix part. And so this Wegener's conjecture was proved to be correct, like the Wiegand Dyson-Miller conjecture. If we just assume the magic element has the second moments and there's all the conditions. So if you assume the magic element has this, of course, this one will stand by more, and if you have a second moments of a magic element, then this conjecture is correct. And we also saw now probably I will not say anything about the edge because I don't have time. And then we will prove that in this case all the eigenvectors are completely delocalized, meaning that this statement is correct. This statement is correct. So eigenvector is basically all flat. So eigenvector will not have a high peak. All right. So and wow. So there are various generalization. It's not a key. But all I want to say is that you can even go below the second moments. And this is something called the fat tail matrix. So if you assume that the probability law of the magic elements called these Levy distributions. So Levy distribution has some special form, but roughly speaking, this is the key you want to keep in mind. The probability of random variable bigger than k is k minus alpha, and when alpha equal to 2, this more or less means the magic. This more or less means this random variable has a second moments. So you can think about this alpha just a number of moments the magic element has. And so what we prove is in this green piece. So you don't need a second moment. As long as there's a first moment, then the whole Gaussian Dyson conjecture is correct. And then below the first moment, there's a transition line, and on this side, one expect that to be this in the solid level, and we cannot prove the whole thing. We prove these regions, and on the other side, there's a part which become the Poisson distributions. So these random matrix statistics actually now one can show that to very general case up to you don't even need the second moment. You only need the first moment of matrix elements finite. And that's all we need. So if you just think about this, because just hearing the result and probably don't feel very much. And think about the random matrix. This magic element, you just flip a coin, basically flip a coin and take plus minus one, and that's what we did. And now you take this one and compare with another matrix which can really Gauss. And then if you compute the eigenvalues, one is if you flip a coin, and the other one is by the Gauss. Now what we are saying is if you look at the eigenvalue, yeah, then the two ensemble, you will not see the difference between them. And especially when this one means this one means this one means the probability distribution of metric element can be completely created. You just need a first moment. I mean, you can when the random variable has first moment, this is probability distribution. The singular, it can be almost anything, as long as as long as you know one. So it's quite. On the other hand, so right now there's not much progress in understanding the proof this line, and this line is quite important. This line is called the mass transition line. So, but in any case, so this was. This model was proposed by somebody in actually somebody in mathematical finance. In short, so anyway, all right. So I want to say more about eigenvector. I want to say more about eigenvector. And now the eigenvector, because the eigenvector has. There's a question about eigenvector, which was I was talking to Mark few years ago, trying to ask you, look at this question. But I will tell you why. So I go back to, so now if you flip a coin like plus minus one, put on the match and you compute eigenvector. And the other one, in the Gaussian case, the eigenvector just because the symmetry is really an orthogonal group. So this one, when I write here TOE, this means that it's this eigenvector is the distribution of the eigenvector with respect to TOE. This means it's SON, it's orthogonal group. So, and now you compute eigenvector. So what we are saying is, if you look at the eigenvector, and then if you take a test vector, test vector k dimension, and you project an eigenvector of this test eigenvector, then if you compute this one with respect to the orthogonal group, or we compute this one with respect to eigenvalue, the ensemble of the random matrices, then actually the difference is quite small. So this means that the eigenvector for random matrices, the probability of the eigenvector, the probability law of the eigenvector is really given by the orthogonal group. This is, but you know, so it's just so let's think about for a moment how you want to formulate this question. Suppose I mean, this was the question I asked myself. Now, if you have an eigenvector is n eigenvector, each one is n dimension. So you have an orthogonal group of very high dimension. So now this orthogonal group of very high dimension. Now, how do I say the Cartesian distribution is given by the orthogonal group? Of course, you can say that the probability law of this eigenvector exactly converge to this half measure of the orthogonal group. But this is impossible because it's such a high dimension. Dimension n goes to infinity, and then to want the probability law completely converge to orthogonal group is definitely impossible. But what you can do is you take an eigenvector, you project to the finite dimensional space, and then you ask that this projection to the finite dimensional space is the same as those given by the orthogonal group. This is the same. So this statement is the projection into finite dimensional space is will converge. And this was correct for large class of random matrices. So let me not to say exactly which class, but actually it's actually much more than weaker ensemble. There are many different ensembles also correct. So this is our basic result. It's a finite dimensional distribution of eigenvector. It actually becomes the orthogonal uniform distribution on the orthogonal group. Fine. So now how do we do this? So now this random graph, I will not say anything because for random graph, it's probably it's a small time for me to say something about random graph. So let's just focus on eigenvector. Now, so why do I actually this was the question I was trying to ask people in differential geometry to see that if you have any idea, something to be done. So the idea, the key, the proof of the result I just mentioned previously is for study the metric Brownian motion. So you look at the metric element, each metric element is given by Brownian motions. And then this is metric Brownian motion. And you don't have to subtract this, you just forget about this. So it's just each metric element is a Brownian motion. So it's B of T. B of T is a matrix, and each metric element is a Brownian motion. I say symmetric, this means that I and J and I, they are the same. Okay. And then you can forget about everything else I made it here. But now if you look at this dynamics for the metric elements given by Brownian motion, and then the eigenvalue is given by the so-called Dyson Brownian motion. So the eigenvalue has the equation by itself. But then you look at carefully, the eigenvector also has an equation. The eigenvector also has an equation given by this. And now if you look at this equation, you probably feel that this is such a horrible nightmare. And this the case eigenvector. You take the derivative case eigenvector. Now this BKL independent Brownian motions, and this K will depend on L's eigenvector, and with the denominator under K minus under L. And then there's another part, which is the drift part, is K, will come back to K here, and number K minus number L squared. So this is, this means the K's eigenvector will depend on L's eigenvector, depend on everything else. And it looks like this. And now, so how can something like this, and I feel that there's any possibility to connect with differential geometry. The reason is because if you take out this lambda K minus lambda L, you replace this coefficient by 1. If you replace this coefficient by 1, then this eigenvector flow is the same as the Laplace operator. It's the heat equation, the standard heat equation on the orthogonal group. So the question is, you have something almost like heat flow. And the heat flow with some twisted heat flow on the very high dimensional orthogonal group. Then can you estimate the heat kernel of this flow? The question is to understand the the heat kernel. Well, some estimate of this flow. And this flow I have written from a multi-language, but one can rewrite this into the second order differential operator. But I didn't write it, but you could have done that. And so the question becomes, you have a flow on the orthogonal group, and then the question is how fast this flow will converge to a hard measure on the orthogonal group if you start from some initial data. So this is really a pure analysis question. The only thing unusual is the dimension n is huge. I mean, you're interested in this problem and angles in billion. So now, I don't think I have that much time to talk about it, but roughly speaking, the way we deal with this is a following. So look at this eigenvector flow here, and now I look at the projection into the test vectors. And now I look at this projection into test vector, and then I compute just a second. So I define the moments. So I take a second moments, and then of the eigenvector, and now I start to look at different eigenvector and I compute the expectation of the high moments or various programming moments. And this becomes a very complicated set of equations. And I'll show you. And this is just not impossible to follow. I just want to show you that the dynamics is so complicated. This was just a few cases. You can see the different colors means the test is different vectors. And the dynamics is actually extremely complicated. And what we did was we have analyzed this very complicated dynamics and to look at the moment and see get this result. Get a result that this expectation will come into our measure starting this way. But I feel that there may be some intrinsic ideas that you don't have to look at these moments for. And the other thing you can look at this directly and look at the heat equation problems in high dimensional orthogonal group and see if one can do something about it. This is what I was with this student, this Jack, this Masonic. He actually was visiting CPS for half a year here. I was here, and this student, because what I did with Paul Bouquet was one eigenvector case. And then for many eigenvector, I did this with this student. And the key idea I find with Bouquet about one eigenvector. Actually, we did this when he was also visiting here. Actually, I was still remember we was in the class at Pennsylvania, talk about this problem. And came up with the idea of look at the moments. And then later on, I think about 5 years later or something, this Jack Masonic, he was visiting here for half a year. And we were trying to solve this problem by using, by trying to solve this equation sort of more or less exactly. And we couldn't quite do that. And he was here for a whole semester. a year for whole semester. You see this test vector is V1 to Vk, and he was doing the various case K to 1 or K to 2, K to 2, and in some special cases, spend a lot of time here trying to do this problem. I feel that it's almost impossible to do this case, but in any case, just keep on doing it, and at the end, it's possible to completely finish this, but still based on this idea, look at moments. If you look at moments, the problem becomes quite complicated. So it's not a nice intrinsic proof, but it's quite complicated argument. So I would like, if there's anyone who finds your geometry interested, very much like to see that whether one could do this by a more intrinsic method. All right. So now, so let me try to go to the part of this. You can see that. Sorry. Some sort of heat kernel type, some sort of heat kernel decay type estimate here. Anyway, all right. So so now, so let me just say a few words about exactly what exactly object we are dealing with. Besides this flow method, the other object we are often look at is sort of green function, or the green function. Green function of resolver is defined to be 1 over h minus z. And h is symmetric, and these are complex variables. And then the problem is easy when eta is this z is e plus I. Eta is small, it becomes harder. And e is inside the spectrum. And now if you take the green functions, you take a trace, it becomes all the eigenvalues minus z over, becomes like this. And this is the sort of Stiger transform of the eigenvalues. So the probability measure of the eigenvalues, and do the Stiger transform becomes this. So you know that once you know the Stiger transform, you know the eigenvalue distribution quite well. And for example, if you look at the imaginary part, so imaginary part of this quantity 1 over lambda g minus z is eta over lambda I minus e squared plus eta squared eta. So then you can see that just imaginary part, it will start, if the eigenvalue are here, it will start to look like this. So here it is. So if you understand this, if you understand MN, then you understand the eigenvalue location quite well. And not just that, if you just look at this green functions a element, take imaginary part, it's still the same as this one. Oh, sorry. But then instead of times, but then you look at it, you have uj and a squared, and this a, the uj is the j's eigenvector. So you can see that the green function also carries information of the eigenvector in this way. So you can see the eigenvector size are hidden here. So once you understand very well this MN and also this GAA, and then you know very well about eigenvector distributions. But typically this eta is to be bigger than the eigenvalue space, because once it's too small, you'll become something like that. And this is a function like this is almost impossible to track. So when you think eta become bigger, it's become flat. This become nicer. And then you can see that the standard is for the semicircular law, you will find that this Stier transform satisfies these quadratic equations. So it becomes the whole random matrices, a lot of ways is prove that for the vegan matrices, you satisfy this quadratic equation 1 plus cn and plus n squared and equal to 0. Small errors. Okay. All right. So so I will not do this, but I'll just tell you that the vegan semicircular is really just prove this Stier transform satisfies this quadratic equation. It becomes quite easy. Well, I mean, easy is relatively. Okay. So so this is the proof. So maybe I will not do it today. And now I want to say about more about the Cherenkov postural law, which is if you go to any statistics textbook or something, this almost is everywhere. By the way, this postural is from Frank. He was working on I also don't understand why he look at this problem, but you know, the vegan was studying this vegan semi-set, this vegan matrices, and Pasteur has idea. You take a matrix because you know this matrix is not symmetric. This X is not symmetric, X mu I, but then you start from X transpose X. If you look at X transpose X, this becomes the sample covariance matrix. So Pasteur asked the same question as vegan, but in the case of sample covariance case. And now, if you look at Lachenko Pasteur, it probably appeared at least he appeared a few hundred times every year. So and also everything the Pasteur did about this sample covariance is not that difficult. If you understand the vegan's case, you can also understand this quite well. So it's remarkable that this spatial class becomes so it's called sample covariance matrix. And the reason it's important because statistics it almost always has a match of this form. X transpose X, and there are some match in the middle, and it's called sigma. And then for the sigma is probability log given by pi. And then if you look at the spatial transform of the eigenvalue of R, you satisfy this equation. And this equation is called the Marchenko-Pasteur. This is sample covariance case. And now, so why am I talk about this? Is because we also do the nonlinear case when the matrices, because you know, so far all the matrices it's needed. And so when I say nonlinear, what does this mean? When I say nonlinear means so now I take vector, n vectors with d dimension, d sort of high dimension. And now I can look at the inner product of a j's vector and the i's vector and the j's vector. So these are ID case. And here I'm drawing a uniform for speed. So you take an i's vector and j's vector, and these are inner products because we are writing this for more engineering, so we use the transport. But this will be the inner product of the two vectors. And then you times the square root of d just to normalize it correctly. And then you apply a nonlinear function. And this nonlinear function is called kernel function. Sometimes called activation function. And then you divide upon the square. So if this f of d is identity, just f of x equal to x is a linear, then this becomes sample covariance matrix. And now each metric element, you apply a nonlinear function, this becomes a nonlinear models. So you can see that this was exactly this one layer of this artificial neural network. There one layer of artificial network actually, but this is exactly the quantity you are studying. All right. So now, this is the quantity you are studying, and now how do we understand the eigenvalues of these models? And so what we find is the following. So you take this nonlinear function, and then you write this as a spherical harmonic function, decomposition into spherical harmonic functions. So the QK are case spherical harmonic functions. This is called actual spherical harmonic polynomials. Okay, from the L and just decompose into a orthogonal polynomial, and then so there's a coefficient of the orthogonal polynomial. And now the next thing is so if you look at this n and the d are all in high dimension, n is number of samples e to the L, and this L is an integer, and L can be 1, 2, 3, or some arbitrary numbers. Suppose n and the d are these relations, and then we find that the spatial transform of this nonlinear model, we can actually find set by equation given by this. And this equation, this coefficient gamma A, gamma B, gamma C, the gamma A is exactly the coefficient of mu to the L. So what is mu to the L? Let me remind you, mu to the L is this expansion of this this function into the orthogonal polynomial is a coefficient in front of the orthogonal polynomial, and this k becomes L. This is mu L squared, this gamma is mu L squared, and the gamma b also depends on mu L, and with some slightly modification. The key is gamma c. The gamma c is mu k squared, and mu k squared from L plus 1 to L is summed together becomes gamma c. All right, and so this means that we are able to identify the probability law of this nonlinear case, because once we show that it's said by this equation, you will recover the probability law. And also, in terms of probability statement, we also have this linear transform, this measure A, will convert a different condition with MZ. It's some high probability estimate in this form. I mean, don't worry too much about this exponent. So this measure means this MA will convert to MZ in some estimate. All right, and this Lu is he's in double E, and he was quite interested in this question. So we talked for a year and try to figure out what's out of this. And now, so the meaning of this result, I will probably end this slide earlier, but that's okay. So meaning of this result is if you look at if you take this nonlinear function, decompose into the orthogonal polynomials, and this orthogonal polynomial is the coefficient mu k, then you can rewrite this match nonlinear match as the sum of mu k of ak. Each ak is given by this inner product with orthogonal polynomial here. And now, so this is our original model. But on the other hand, now we define a separate model. This separate model is b is the same as a with the same coefficient, but bk only from k from L to this small L to capital L. And let me remind you, the small L means small L is here. This n to the n over d to the L. So this is L. N is of the order d to the L. This is the L. All right. So this is the d to the L. And now you can mu L. Mu L is a sum of covariance matrix, which is the Gaussian case. And then for L bigger, for K bigger than L, we just put the Gaussian orthogonal ensembles. And now, actually this one and now all the BK are independent. So what I'm talking about is, suppose you construct another models, and for these models, the mu L is a sample covariance matrix, and then everything else are Gaussian orthogonal ensemble. And then you assume that they are all independent. Then you find that this B, the MB was satisfy the previous equation. Previous equation means this equation. This equation was satisfied by MB as well. So the idea, what we are saying is that if you want to understand these models, what you have to do is replace the AL by BL, and everything from L from K become L plus 1, so we just replace by Gaussian orthogonal ensembles. Then your nonlinear model will be equivalent to the summation of a sample covariance model plus a Gaussian orthogonal model. So that's the idea. So the nonlinear case, you can actually compute it. You can actually compute them by sample covariance plus a Gaussian orthogonal ensembles, and then with the coefficient given by the expansion in the orthogonal polynomial decompositions. That's the idea. So this answers the first question in this nonlinear setting. And now there are many questions one can ask. The question is, we don't know anything about local statistics. We don't know anything about eigenvector at all. So for both eigenvector and both this fine structural eigenvalues, we don't know. And also we do the spherical symmetric case. We can also do the Gaussian case, but we still don't know how to do completely general non-Gaussian case. And I also forgot to put one more point here. One more point, and this is just one layer. You can also ask the question of the multi-layers and whether this whole thing can be extended to the multi-layer case. And I think in multi-layer case, I don't know any partial result at all. So so I think the whole thing is completely wide open in the multi-layer case. And especially if you put the eigenvector, then basically just nothing is known. But actually, even in the Gaussian case, I don't know about eigenvectors is at all. It's completely unknown. And the reason, so let me explain the reason why the question suddenly becomes much harder. And I don't have to just explain it here. So if you look at this metric, here is x, I, x here, and you take the inner product q, k. If you look at this, actually it doesn't matter any nonlinear boundary. Now the trouble in putting nonlinear boundary here is that you lose the independence anymore. So the metric element, their dependence on each other are just very, very complicated. It's you are dealing with the question of a matrix. The metric element is a very complicated correlation. And so once you have very complicated correlations, then there's not very much we know about how to deal with the random matrices. And so that's why it becomes sort of quite complicated. So and then you can imagine that if you have a two-layer. So if you have two-layer, take this one and you multiply another object here, you take another nonlinear function, then the correlation will be even more complicated. And so I think it's quite interesting question to start to look at this in the multi-layer situation and see what's going on. In any case, it's almost completely open area. All right. So so here is the conclusion of today's talk. Is there are some open problems. It's the other type of metrics like this. It's U star XU, and U is of unitary matrix and in the power measures, and this type of model is also not known. And also I think for those of you who are more interested in applications, what the key message is when the matrix is to a nonlinear case, it's completely open. Since there's not much is known here. And so it requires completely a new understanding. So that's really the message here. So I think I will not say anything about this more crazy things. But roughly speaking, I just want to emphasize that probably this application and also the neural network applications, most of the matrix theory, we still don't know how to extend to these cases. Thanks a lot. Thank you.
Thank Professor Yang, because we have some friends online to help them hear clearly. So our question must use microphone. So if you have a question, first raise your hand.
I have one question about the unique algorithm. So if I remember correctly, this is still an open problem. However, Professor, you mentioned that we have a probabilistic version of this algorithm theory. So my question has two parts. The first part is this probabilistic version proved through random matrix theory? And the other part is this problem solved completely, or is there still any the question?
Oh, I see. So what we are doing is we look at the differential geometry question. The question is completely open. I don't know. I think only some special cases of, I cannot say special, there are only cases with some arithmetic structure of one know the answer. Okay. So yeah, again, there was a few results in this was if you look at this as a mathematical question in geometry, this problem is completely open. there's no general theory. The only thing that there are a few cases people can do, the manifold, this complex manifold, some arithmetic structure. Then for that, there are some, they are very resolved by Lindenstrauss and also by, and also for getting some result and also, what exactly is, and there's some arithmetic case, one has some result. So what we are doing is, we just borrow the terminology. The borrow terminology, we usually analog in the probabilistic settings. It means the eigenvector are prime. So here it's eigenfunction of prime, and here it's the same eigenvector of prime. So these are, we're just using this analog using this name. Okay, so first of all, this is one of your question. And the second question is how do we prove this? Now, to prove this, like the way we prove this is borrow. We prove this is couple statements probably I should have. So here you see that we prove that the eigenvector, the projection into test vector is the same as the solvent rule. So once we can identify the probability distribution of metric of the eigenvectors elements, then we can prove the law of large number. This tell you the probability law of each eigenvector component. And if I know eigenvector is each component of the probability law, and I also know they are dependent, then I can prove the law of large number of the eigenvector. The law of large number of eigenvectors becomes QE statement. So that's how we do it. It's something we did in quite a direct way. It's through the identify the probability distribution of the eigenvector and also their high moments, their correlation. We can study by looking at this quantity, and from here we can prove that this quantity real calculus. Actually, they are. I think one of my students actually now they are trying to prove that they can do this. They can do the essentially here. I didn't prepare this note actually. If you divide by 8, it's given lower than something. You can also divide by square root of 8 to prove that it becomes Gaussian distributions. This I think this for regular matches, and there are many cases this can be done. The typical is if you have a K, if you have different eigenvectors. Statement about one eigenvector is the statement about many eigenvector correlation. It becomes much harder. That's the best.
Any other questions?
So in your expectation estimate, you have n to the minus epsilon power, epsilon. So that epsilon depends on the type of random matrix.
No, the epsilon is arbitrary positive number.
Obviously, oh,
You can prove this for arbitrary.
obviously epsilon.
So it's just for any epsilon, there's estimate.
Oh, for any epsilon, you have the estimate. Okay.
But then the coefficient in front of estimate depends on epsilon. So so for example, you want to do this. So there is epsilon here, and then you can say the probability that this one is bigger than that is less than some Henry minus high power, but then this Henry minus say Henry minus some power, and in front of this coefficient C and epsilon. C of epsilon. The epsilon becomes smaller, the constant becomes bigger and bigger. So this kind of statement.
Oh, thank you.
So epsilon is actually actually the optimal one is Henry minus 1 times log n. I think the optimal one is Henry minus 1 times log n squares. This one is not optimal. The best estimate is Henry minus 1, I think times log N, it's N minus one and log N.
Oh, can you look in?
N
I
minus
don't
one,
know.
yeah, N log N is the best result. But we just did N minus one ourselves. You can do some pipe on all the stuff.
Thanks.